Jai Hind all. Myself Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. Today in this video lecture, we will discuss about the topic taken from Digital System Design, the subject code as prescribed by Abdul Kalam Technical University, Lucknow is KEC 302. Here we will take the topic from 4th unit, that is TTL Logic family. TTL logic family is transistor logic family, and in which we design the circuit using transistors, or the circuits are especially the digital circuits, right. We will go through these topics. First of all, I will introduce you with the logic families introduction, then all the logic families which are assessed by some parameters and their performance characteristics. The parameters will be discussed for the logic families, and then finally we will discuss the TTL logic family. Now, there are various logic families, and they can be broadly classified according to the technologies they are built with. Like, some technologies are based on transistor logic, some logic families are based on diode and transistors, few are based on ammeter coupling logic, and the one more logic family which is transistor logic, that is purely based on the transistors, and the last one is the CMOS logic. So this CMOS logic is basically based on MOSFET, and in which we are using PMOS as well as NMOS. So combining these CMOS logic, we can make the digital circuit, that is NMOS plus PMOS. So whatever the circuit I will make for the NMOS, I can reverse the circuit for the PMOS. So if NMOS circuits are connected in series, then PMOS will be connected in parallel. Now TTL and CMOS logic families are most widely used IC technologies. Here transistor logic is not a very huge technology, because it implements on a single chip. There are less number of transistors to implement a logic family, but in case of CMOS there are millions of transistors that can be incorporated on a single chip, so make it a very large scale integrated technology. So this CMOS logic is basically belongs to VLSI, and the transistor logic is basically, it is based on MSI, medium scale integrated circuit, or not millions of transistors, but less number of transistors are making this circuit, like 50 to 100 or 100 to 200, that's all. And in the labs you must have seen some AND gate OR gate ICs, and that are purely TTL logic ICs. Now TTL and CMOS are widely used, whereas each family is having subfamilies too, and they are assessed by their various parameters, and these parameters are speed, the dissipation of power, and dependency on the temperature, also the supply of voltage level and current level. So these are few parameters by which these families are assessed. So coming to the performance characteristics of logic families, if I come to this particular point, then I have to define some equations, some definitions, or some sort of explanation for the logic performance characteristics. So here the first parameter is VOH minimum. So this VOH minimum, so these parameters, see, VOH, VOL, VIH and VIL all are being talked between two gates. That means, as an example, if I say I have taken this gate and this gate, what I am doing is I want to talk the state or the current and voltage between the two gates. So if I am very well aware of the current and voltage level between the two gates, then I can assess some performance of my given logic family. And if two gates between them the output is 1 and there is another case when the output is 0 or low. So in the figure we have shown two type of scenarios in which the high state output and input has been considered between the two gates. First gate is NAND gate and second gate is NOT gate. Similarly, in the other scenario, there are again two gates and we are talking between the gates. Between the gates, the input is high and the output is also high. Output will be for the previous one and the input will be for the next one, right, as shown in the figure. Now coming to the parameter. So these parameters VOH minimum is defined by logic 1, okay, logic 1 state. Suppose there is a logic 1 in the between the two gates, as in this case we have high, output is high and this output is going into the input of next gate. So we are talking for the one state between the two gates. So here the VOH minimum is the minimum voltage that the output in the logical 1 state under defined load conditions. That means this output should be to that level the another gate should identify or another gate should recognize under the given load condition. This is the definition for VOH minimum. Similarly, for VIH minimum, that is the minimum voltage required at an input to be recognized as one logical state, right. So VIH minimum, that is it has to be input to the next gate, but it has to be recognized by the next gate too, and that because the output is high, so that output or input voltage should contain the minimum threshold that the next gate can recognize it, right. So this is how we define the input and output of high state minimum, right. Similarly, VOL maximum. Now if I am giving a low input to my between the two circuit, then this low input should have that maximum value that the other circuit can recognize it, okay. So that level for minimum or low output, okay, the minimum voltage that can be applied so that another gate identifies it as a 0 input, this is known as VIL maximum, and that should have some value so that it can be recognized by the next gate. So in that way I can say VOH minimum is minimum voltage level at an output for logical 1 state under defined load conditions. Similarly, VIH minimum, the minimum voltage required at the input to be recognized as one logical state. Similarly, I go for VOL max and VIL max. These are maximum because output and input are low. So they should have for for any output to be recognized as 0, the output should be to that level that it has to be VOL maximum. What amount can be given for defining it as a 0 or low output or input? Next, the performance characteristics in terms of current for low and high states. Here again, what we are doing is we are talking between the two gates VOL low, VIL low, and the current is VOL low and VIIL low. So here there are two gates, one is NAND gate and another one is NOT gate. The propagated bit between the two gates is 0 in this particular case. Here it is the positive voltage and this positive voltage will go here, right, and this VOL should have that minimum value so that other can recognize it, that is IIL. So if this current is going like this, another current will also go like this, see IOL and IIL, right. Now, so coming to the definition, current flowing into an output in the logical 1 state under specified load conditions, current flowing into an output in the logical 0 state under specified load conditions. See, all the definitions are very easy. Similarly, IIH, current flowing into an input when a specified high level is applied to that input. Next, current flowing into an input when a specified low level is applied to that input. So, we have 4 definitions which may come in your examination, or it is better you should know it for defining the circumstances between the two gates. Now, some more definitions which are frequently asked in the examination. First is fan in. Fan is number of inputs for a particular gate, that is defined as fan in. One gate can handle how many inputs for the correct output, so that your output is not to be disturbed at all. Similarly, for fan out, see, some logical circuits are belonging to only one logic family, and there are more circuits which can belong to one or more logic families. So here also we are considering the number of inputs for the various logic families, and loading factor or fan out is the maximum number of logic inputs so that output is not disturbed. Similarly, the power dissipation, power required by the logic circuit for desired operation. And then figure of merit. Figure of merit is nothing but delay time into power, that is P tau, where it should be in milliwatt and this should be in nanosecond. Okay, this should be in nanosecond and this should be in milliwatt. After discussing the propagation delay, one more important point is there. The propagation delay, logic signal always experience a delay. See, we are giving input to the input of one gate, and then we are taking the output, right? We are taking the output so that the propagation delay is there from input to output through the gate. There must be some delay for getting the output from the input terminals according to the gate function, right? The two propagation delay times are defined as low to high and high to low. See, whenever there is a switching from 0 state to 1 state, there will be a delay time, and from high to low there will also a delay time. That means the time taken by the input from 0 state to 1 state, that is the switching time, which is also to be defined and these are important parameters for calculating the propagation delay. Here propagation delay in terms of P high low to P low high, okay, that will be P TPHL plus TPLH upon 2. Okay, high to low and low to high. Okay, why we are taking this at a 50%? Because we have set some threshold to. Now coming to the noise. So some noise is a random type of function, and there may be so many reasons the digital circuit are kept in the noisy environment, like they are kept in some magnetic field or and so there is a noise in the circuit which can affect the function of that particular circuit. Noise immunity is a measure of checking the circuit's ability to tolerate the noise without changes in the output voltage, and here we define these noise as noise margin. In the figure, if I can see, there are two figures. So what these two figures are mentioning? These are two definitions, VNH and VNL. So what is VNH? There is a logic 1. For logic 1 to be identified, there is some minimum voltage that should be given for a logic 1 to be identified or to be recognized. So that is known as VOH minimum. So I have mentioned this VOH minimum here. Similarly, for logic 0, that maximum level where logic 0 can be detected, and if the level crosses that logic 0 VOL maximum, maybe it can be detected as logic 1. But what we do is we keep some disallowed range 2 between VOH minimum and VOL maximum, right? Now, so that how to calculate this VNH and VNL? Let's say I am not getting this minimum value, but I have got this minimum value just because of noise. So noise figure can be calculated by VOH minimum minus VIH minimum, and similarly my output level for 0 has been raised due to noise, and here I can calculate VNL is equal to VIL maximum minus VOL maximum. So these are two definitions which we should remember for defining VNH and VNL. Now coming to the TTL family, first family which we are going to discuss about, the TTL gates using plus 5 volt, 0.25 volt supply and are capable of high speed operation. So there are 600 different logic ICs are available, and they cover approximately all the digital function that can be performed. So most of the TTL circuits have similar structure. There is one difference. Hold on. The NAND gate are designed and the OR gate or NOR gate are being designed using two different methodologies, right? In TTL2, first is the input will be at cathode of the PN junction. A high input will turn off the junction, only a leakage current is generated. A low input in terms of junction, relatively large current is generated. What does it mean? It means the high input will turn off the junction and low input will turn on the junction, right? That we all know. Most TTL circuits have type of totem pole output configuration. There is one configuration which needs to be covered, that is in totem pole there are two transistors and they are connected with a diode. Due to this diode, one transistor will work at a time, right? So there are two speciality of TTL logic families. We are using this multi-emitter concept and the transistors are basically of multi-emitter 1, right? So transistors are multi-emitter transistors. Here in this figure, I can see this Q1 transistor is nothing but a multiple emitter transistor, right? One more term which we are using here and that is very important, that is totem pole arrangement. There are two transistors we have taken, one Q3 and another is Q4, right? The Q3 and Q4 are connected with diode. There is one diode D1 which has been connected through Q3 and Q4. Okay. D1 is at the emitter of Q3 and D1 is at the collector of Q4. Okay. And these both transistors we have taken as NPN transistor. So there are two things which we need to remember. First is the multiple emitter transistor and second thing is totem pole arrangement of transistors, right? Now coming to the basic operation of this TTL NAND gate. We have used some resistances also, this base at the base of Q1, the collector of Q2 and collector of Q3, right? So some biasing has been given for plus 5 volt, right? And this Q1 has been given 2 emitters. Now we will provide inputs for these 2 emitters of Q1. This is the biasing which was required. Now coming to how it works. Since emitter base junction is a diode and collector base junction is also a diode. So what we have done is we have represented it base and this is emitter E1, this is emitter E2. So this is emitter base junction, we have mentioned it as D2 diode and this is as D3 diode since D1 we have taken here in the totem pole arrangement, right? So here we go, this is base, this is collector, that you already know. Now if I give 1 1 to both inputs A and B, that means I am giving A to be plus 5 volt and B to be plus 5 volt for logic 1. For logic 1, both I have given at plus 5 volt, at D2, at D3 for both. Now plus 5 volt and plus 5 volt, remove one circuit and see whether your transistor will work or not. It will definitely work because one emitter is out of picture but another is working as normal, right? So my first case would be A and B both are positive and there is no such diode equivalent circuit. It is there but not to be shown while explaining the answer. So here D2 and D3 two diodes are connected. If I give a positive voltage on A and B, plus 5 volt on A and B, then what is going to happen? See, if I will apply a negative bias to my positive, since N is negative, bias has to be given and it should be negative. If it is negative, then it is forward bias, and if it is positive, then it is reverse bias. So this plus 5 volt will make it reverse and this will also make it reverse. Now if it is reversed, then what will happen? All the current will be IB only, right? And we have A1 and A2. We can take now A and B both are at positive value. If both are at positive value, D2 diode is off, open circuit. D3 diode is off, open circuit. If D3 and D2 both are off, then what will be the scenario? If D2 and D3 both are off, what will be the scenario? That see, I have removed this particular transistor. These two diodes are as well, right? There is no problem at all, and Q2 becomes on. Q2 becomes on, and while Q2 is on, it will definitely on the Q4. Please repeat my words that if Q2 is equal to on, then output will also be V on, and if Q3 is let's say off, Q2 is let's say off, then Q4 will be automatically off. So Q2 and both are connected with each other. Now coming to the part where both are on, Q2 is on, making Q4 to be on. Just because of this is on, this Q3 will be open circuit. Okay, and if it is open circuit, input will be 0, because there will be a short circuit due to the on position of my Q4. Right. Similarly, what we can do is, if let's say Q2 is off, for some reason this Q2 becomes off, then Q off, and if it is off, then it will be open circuit, and all the voltage which we have applied as plus VDD, that will appear across the output voltage between the output node and the between the ground. See, this is the output node. If it is open, then this is the one ground and this is one output. So this output will become high for Q2 and Q4 both to be off. So for 1 1, what I am getting, this should be 0. If it is on, here it is on, then Q4 is on. If Q2 is off, then Q4 is off. This is the catch point of this TTL NAND gate low output logic. So A and B both are low. If A and B both are low, then these are like, you can remove this particular part from the circuit. We can remove it, and all the current will flow across this thing, right? If both are low, then what is going to happen? This should off and this should on if both are low. So here it has been written that A or B both are low, Q4 will become off, because Q3 is on in this case, and this Q3 is on just because of Q2 to be on. So Q3 is on due to Q2 is on, and all the reverse bias circuit will flow through the circuit. Now characteristics of TTL, there are few characteristics too based on bipolar transistors. So one of the most widely used families for small and medium scale devices, as already I have explained. Typically it can operate for plus 5 volt supply, not more than that. Noise immunity about 1 to 1.6 volts, and many forms are have been made, and they have been optimized, and they are being optimized for speed, power, etc. High speed versions are comparable to the CMOS, and low power versions are down up to 1 milliwatt per gate. So these are some practical characteristics of TTL. In the next video lecture, we will discuss the ECL.